Okay. We were talking about, I don't know how far we went. Could you please bear with me for a second? I don't know what this, hold on a second. Okay, let's start this way. All right, here's where we're at. Okay, I don't know how far, I don't remember how far we went with this. We talked about the condition number and the norm of a matrix, right? And we started talking about LU decomposition. Yes, no?
I think we started talking about it.
LU decomposition or?
Actually, I think we ended right before that.
Okay, so this is where we stop. All right, just in case. All right, as in the case of vectors, we define the norm of a matrix in a similar way. This is the L2 norm, which is the sum of the squares. There are many other ones, as I said last time. All they have to satisfy are the conditions for a norm, and they're very vague. Wait, not very vague, very general. It has to be a positive number, but other than that, it has to satisfy the triangular inequality and a couple of other things. But other than that, anything works. And any of these are the norms. And the condition number is defined as the product of the whatever norm you're using of the matrix itself with its inverse. And it's a measure of how much the image of the map varies with changes in the input. Basically, the condition number is related to the ratio delta y delta x, where x is multiplied by a. It's basically y is the map of x. So if we change a little bit x, we expect y not to change very much if a is well conditioned. If it is not well conditioned, then this ratio can be very large. If it is in fact singular, this is an infinite number. If it generally is very large if the matrix is ill conditioned, meaning it has a lot of entries of varying orders of magnitude. Okay, we can show this relationship here, which is again, it's related to the changes that may be related to the matrix itself. Remember that we're always interested numerically in these things for a number of reasons. First is because of truncation errors that take place in the computation, but very often numerical problems arise from practical problems where the parameters, let's say the parameters defining the matrix A or the input vector X that is dealt with, that is being mapped with A, they may not be very well, they may not be precisely known. So it's very important to have this an understanding of how sensitive the problem is and how well posed it is and how sensitive it is to variations in the data or the input. Anyway, all right, we saw Gauss elimination. We saw that we can do some pivoting there to try to bypass some of the problems. But the problem with Gauss elimination is it's a very time-consuming process, and it introduces a lot of errors if the matrix is not very well conditioned. An alternative and a better way is to do the so-called LU decomposition. Now, LU decomposition is very simple. This, and the LU stands for lower and upper. So we split A into these two lower triangular matrix and an upper triangular matrix as a product like this. The appeal of something like this is it's kind of obvious. I'll talk a little bit later on about it, but it's appealing to be able to do this. And the question is, can we always do it? How can we get these numbers in an efficient way? It's not enough that we can do it, but we need to be able to calculate these numbers, L's and the U's, in a rather efficient way. First of all, why would we want to do this? First of all, we know that the determinant of a matrix is equal to the determinant of the product, but depending on how many arrangements we have made, the arrangements we've made, we have a -1 sign raised to the p power. If we multiply all these out, right, the obvious way to get to this is as follows. This is equal to A11. I'm not going to write them all. A1, 2, etc. Right? So the way to see if this is possible is we just multiply it out. Okay, we have this times the first column, L1 U11 will give me A11. If I multiply this column with this, it will give me it should give me A12, and I should be able to solve for these. So that this can be done is pretty obvious, right? It will result in n squared plus n equations. All right, we have here the matrix is n by n. Here we have half the entries from here, half the entries here, and then but there is an overlap because of the diagonals. So we have quite a bit of freedom in choosing these parameters, these numbers, u's and the l's. And so we can write these equations like this. All right, so that's pretty straightforward. This is what you would do if we were to try to do this. The question is, how do we do it in a most efficient way? Because if we're going to replace the original equation of n by n equations with now n plus n squared equations, this is not a great advantage, is it? All right, because in order to solve this, we have n squared equations to solve for the n squared unknowns of the splitting part. Okay, before we even get to solving the AX equals B. So, so the point is, can we do this in a smart way? And it turns out that we can. All right, using Crouch method, we distinguish between a number of cases. Here you see the obvious one. All right, as I mentioned, you realize that the first equation U11 times L11 is equal to A11. That cannot be solved because neither L11 nor U11 is known. Is there any way to rearrange these or do something about these things that that will be able to allow us to solve this? In any case, let's write these equations out. And basically what we have is three types of equations. For I just less than j, we have Li1. This sum equals to the entries A. All of these are Aij's, but the only difference is whether the first index is smaller than the second, or equal. That's the diagonal terms that we have. These are all the diagonal terms, and whether we have I greater than j. So this is the only difference, and they vary because they're different because of the location of zeros. Depending on whether we're talking about this portion of the matrix, we get one type of equation. If we're talking about this portion of the equation, we get a different form. They're similar, but they're different. Right now, there are n squared equations. Right, that's what we have. We have a is n by n, so we have n squared equations, and n squared plus n unknowns. Right, so so that seems to be that there is a problem that is not uniquely solved, and it isn't. But it also gives us a freedom to choose n of these, so as to make the algorithm fast and easy. And in fact, that's what Crouch method does. We choose the n unknowns to be the diagonal entries of the lower triangular matrix. So we pick these three, in this case, which is a 3 by 3, L11, L22, and L33 equal to 1. Immediately, you can see the benefit here, all right, and how this thing proceeds. If we make these equal to 1, the previous equation that I wrote, which I just described, U11, L11 is equal, that makes U11 equal to A11 immediately. So that one is already taken care of by a simple equation, basically. All right. Presumably, if we get this, we can get the other one, all right, and so on and so forth. That's the idea behind it, that we don't have to solve simultaneous equations, but that they can solve them in a smart sequence, and therefore with the sequence, if it is done properly, we don't need to know all the all the unknowns at the same time. Okay, so this is what we have. Okay. Having chosen the L11 is equal to 1, we have Crouch algorithm. It's in more detail in the text if you want it. In fact, one of the homeworks, the homework that I'm going to assign requires you to program Crouch algorithm. But you can get the details of it in the text. or the appropriate section in the text. If you don't want to buy the text, or you can maybe copy it from somebody. It's just one page. It's a pseudocode listing. But we'll go through it here. Okay, so Crouch algorithm is a way to do it. That's how everybody does it because it's the best, it's the fastest and easiest way to do it. All right, so it's used to solve for the n squared that we don't know, that we haven't chosen, that we cannot choose. Okay, so what do? For each L, okay, first of all, we set all the L1, Li's equal to 1. So that takes care of the n unknowns, and then we're left with n squared of them. So for each of the j's now, we pick j1, 2, up all the way to n, all right? There are two procedures, depending on whether I, right, is less than j or j is less than I, to utilize the proper equation from here. But other than that, the algorithm is pretty straightforward. So for each j, we do the following two procedures. All right, we use the appropriate equation, 1 or 2, depending on where we are. Okay, to solve for the uij, and we have uij is equal to aij minus l. This sum. The sum is from 1 to I minus 1. All right. The diagonal term is not included because of that it's in here. This is the diagonal term, all right? And so we get that uij from this. Now for the j, for I greater than j, all right? We use the equation 3, which is translated to this to solve for the else. Now this portion is used to find the u's, and this one is used to find the else. The reason is obvious, all right? If you look at the equations here, we use the third equation to take care of for the else, because that's the one that has most of the zeros here. We use the lower i's to solve for the equations to solve for the u's, because that's where most of the u's the zeros are here. So we go back and forth, all right, according to this. If you actually follow this, and this is the trick about this, the tricky part of this, all right? If you follow this, this is the algorithm, all right? And it's pretty easy to program, as you can see here. There is no iteration; it's just a straightforward procedure with a couple of if statements, a couple of do loops. It turns out that the Lij and the Uij needed in 4 and 5. In other words, these guys here needed to calculate Uij, and these things Ukj and Lik here, all that stuff that is needed for the else has already been calculated with the previous calculation. So all the stuff here is basically multiplications and divisions. There is nothing to worry about. The only thing that you need to worry is to avoid division by 0 here in this room, in this location here. Everything else is multiplication of known quantities. These have been calculated. These are given by the matrix, and therefore you just basically go down the row, down these i's and j's, and calculate the u's and the l's sequentially, essentially, if you follow this procedure. Like I said, the only problem that you may encounter is with u, where if you have a very small u to deal with, then you need to do some pivoting. So pivoting is essential to avoid problems here. So we need to rearrange as we move along here. We rearrange the rows of the matrices, but you don't need full pivoting. You don't need to do pivoting on the columns and the rows. You only need to do it to do it on the rows. The other thing that's nice, and this is not relevant these days, but it was in the past, is that the Aij, the entries of A, are only used once for each formula. Once you use it, you don't need it again. They only show up in one place. You don't have many of these here, so you don't need to resort to other ones. Once you use it, you can discard it, and in the original matrix A that you had, you can use it to store the L's and the U's. So you can write the new matrix as this. and so on. In other words, you replace, this is where the A's used to be, and you just, as you calculate the numbers, this was important, as I said, in the older days when computer memory was in short supply. Computers had instead of gigabytes, and you had to worry about how to store all this stuff, especially if you have a large system. Now it's not important, but it's convenient also. I mean, it gives you a proper place to store the stuff without declaring extra, requiring extra storage space. So you can write it this way. Remember, immediately here implied in this is that L11, L22, and L33 are equal to 1. So you don't need to store that. That's part of the algorithm. That's known. It's only the ones that you calculate. And since these are only used once, you can replace them with whatever. As you march along here, calculating these numbers, you can replace the AIs accordingly. All right? Now the problem is, as I said, with pivoting, you need to be careful with pivoting in order to avoid division by small numbers here, or 0, the worst case. All right, and then with the above choice of L11, then the determinant of A also is the product of the diagonal matrices, the diagonal entries of U. This follows from this decomposition here. All right, from this, since the determinant of A is equal to the product of the two determinants, the determinant of L is the product of the diagonal terms. The determinant of U is the product of the diagonal terms. These are all equal to 1, so they don't count. So the determinant of A is equal to the product of the U's. So as you do this, you also get the determinant of A, which was such a tedious thing to calculate using the cofactor scheme. Remember when I mentioned the cofactor formula for calculating the determinant, I said this is the wrong way to do it. Now it becomes obvious that you're better off doing it this way, and then up pops the determinant as well. So that's also very convenient. All right. What else is there? Okay, the last question is whether we can solve this equation. Ultimately, our interest is to solve AX is equal to B, right? Having done this now, the solution of this repeatedly actually is easy. Why? Anybody? Am I moving too fast? Anybody? Can you hear me? You there?
Yeah.
All right. Now, why is this last part important? Not important. It is important. It's important because that's the problem we want to solve. Why is it so easy to do? Anybody? I mean, at first glance, all right. So I replace this, and what do I have? I have this. Okay. This is exactly what we just did. Well, you can see it in two steps. Let's say UX is equal to Y. Then we have LY is equal to B. Right? Okay, now with this assumption, now this can be solved easily because L is lower triangular. It's a trivial thing to solve. Because all I got ones here, and I got entries down here. So starting from the top, I get that Y1 is equal to B1. This is equal to 1, right? Y2, which would be this one, it would be L21 from here times Y1 plus L22 Y2 is equal to B2, right? That's the second equation. This one I already calculated, it's equal to B1. So all I got to do is solve for Y2. There's only one unknown here, so I can solve it. Basically, because it's lower triangular and all these are 0, I can solve for the Y very easily. Once I solve for Y, I go over here and I have the upper triangular part times Y is equal to B. is equal to, I'm sorry. I have that the upper I'm sorry. What did I do here? Yeah, I apologize. I rushed through it. This should be U here. Somebody should have called me. Okay, so all this stuff here involves only U's, all right? But that's what I said is still true. We have UX is equal to Y. I'm sorry, this was fine. Let me erase this. Okay. Basically, the bottom line is we have to summarize it, and then I will do it properly. It's equal to B. Basically, we split it into two sections, and both of these are upper or lower triangular, and it can be solved because most of the entries are 0. So we set this equal to Y, and we have Ly is equal to B. We can solve for Y easily, as I indicated, right? Because this is only lower triangular, and I can solve it in a very straightforward manner. It's as simple as the Gauss elimination back substitution approach. All right. Getting Y, then I have that L. Then I get UX is equal to Y. Now Y is known. All right, and I can solve the same way for X to give me the Y that I have just calculated from here, because U again is upper triangular, so it simplifies quite a bit. All I have to do is just start from going from the last one and start going up until I get all of them. Is that clear? Even though I bungled it up a little bit. Yes, no?
Yes.
So this is a sequential process, both of them involving upper or lower triangular matrices, and therefore they can be solved one at a time, the entries, and so we can solve it for as many times as you want. You notice that once you do this, this only requires pretty straightforward calculations. And if I change B, all I have to do is find another Y in the same way, but it's a very going backwards. Okay, so this is once I get this splitting, then solving it for various B's is very straightforward in 2 steps. All right. So that's the nice thing about this method. This algorithm, and that's why you can use Gauss elimination if you have some reason to do it for that, but it would be sort of the wrong way to do it. This is the dominant. MATLAB has a function that's called LU. And it does exactly this using Kraut's algorithm, and it works the same way as I indicated here. What does it do? Let's say we have an example. Let's say take matrix A, which is 1, 2, 3, 4, 7, 8. It has these numbers. This matrix is not quite singular, but it's not very good either. So if you ask MATLAB to decompose this is 4 by 4. You can do it by hand if you're patient and careful, but that's not going here. MATLAB would do this. It will split it into lower and upper triangular, and it will also give you any permutations of rows that it has done in order to do the pivoting properly. All right. So let's see how we would get this. You can type C. This is the matrix. All right. You type it in. This is the first row, second row, third row, fourth row. All right. And it will give you the result. It's no big deal here. So this is a matrix C. It's always nice to see what happens with the inverse. What happens if you ask for the inverse? It's so painless in MATLAB, so you can just try. So the worst thing that can happen to you is it will just complain. So you get an inverse, all right? You notice that this is a very small number, all right? And this is not very good. It's a 0 practically, but immediately you can kind of tell that you have some round-offs in finding the inverse. But anyway, that's what happens here. This is the inverse. The condition number is not great. It's 139. It's not close to infinity, but it's large. It's far away from 1. but it's not an ill-conditioned problem. It's something that you wouldn't want to use Gauss elimination to solve. All right, so we can call the function LU, and the call for that function is as follows. LU is a function that returns three components. All three of them are matrices. C is a matrix. It has to be a square matrix. All right, and first one is the lower triangular. U is the upper triangular part. That's the first output. The last one is the matrix that tells you the number of the permutations that it did in order to achieve this. So if we do it for this matrix that I just wrote here, what do we get? We get L11 is as expected. We have ones along the diagonal here. All numbers down here. You notice that there is a 0. As expected, the upper part is 0. And we have some small numbers here. This is part of the problem, and there's another and this is the one of the problems. Okay, that gives us the 139 condition number. The upper triangular part is this number now. All right. Again, this is what expected. These are the diagonal entries. These are the 0 parts, and this is what it has calculated to be. These are nice and round numbers. This one is. You see, this is a round problem. This is a permutation matrix, and it gives you a 4x4 matrix that is symmetric. And it tells you how many rows it has interchanged. Which ones? So we can verify the results, all right? We got the numbers, all right? So we got L1, U1. You can verify by just multiplying. And if you multiply it out, you get this. LU gives you this thing. It's not the original matrix. 33, remember, was down here, and 30 was somewhere down here. It doesn't quite match. But that's because we haven't, this is the permuted matrix. All right. So in order to recover the original one, we have to apply the permutation. So we do this by putting P1 in front, and that's the one that permutes. Whatever results we got here is permuted by this, and it gives us the original matrix. This is the original one. You notice that this is sort of reversible for this example. All the numbers come out round. We don't have too much round off for truncation errors because the numbers work out okay. This is not a bad matrix to work with, right? But so we recover our matrix. Now, since P1 is given, the permutation, whenever if we want to solve this problem and we want to solve it with the way that I indicated sequentially as uy equals b, and then lx equals y. If you want to do that, that's pretty easy. But you have to remember to multiply b by p1 in order to rearrange its rows in order to apply the LU. Other than that, everything is fine. And every time you have a new B, you can just repeat these two statements and it will solve the problem for you. Any questions so far? Am I moving fast, or I mean, where are we with this? You guys still there?
Yeah,
How's the pace?
that's good.
I mean, all right, this stuff, you know, you cannot take this down, but you can get the operations proper, you know, in your mind, and you can try this. This is something you could try very easily and play around with it, okay? MATLAB has pretty good, you know, help to get the details of this, but the names are self-explanatory for some of these functions, so we can kind of move along. Okay, so this is what we have. Now we have another example. This is a matrix that you should always know is singular. Any matrix that has 1, 2, 3, 4, 5, 6, all the sequential numbers up to 16, you could make up to 25, 36, whatever. Those are all singular matrices. Okay, these kind of nice arrangements where you just park the numbers here give you a singular matrix. So you can verify this. We can write it. This is easy to type. Okay, and this is the matrix B. Immediately we ask for the inverse, it will tell you matrix is singular to machine precision. It's actually singular period, not to machine precision, but it's in fact singular in an exact way. and it will give you this number here. So, you know, that's just out of curiosity. Like I said, finding the image of a matrix is rarely a good idea. If we find the condition matrix, the condition number for B, you see, is 10 to the 17th. So that immediately tells you what is going on here that you shouldn't have. Now, having said this, it can still be factored into a U form. Trying to solve the problem might give you difficulties. AX equals to B if B is in the wrong place. But on the other hand, the decomposition can be performed as easily. And then if all you sometimes you're only interested in the determinant for some reason or another, then you can pick it up from this decomposition, which is pretty straightforward. So again, we apply we call LU of for this case B, L2 U2 B P2, right? And you write and you get L2 is this matrix again. It's nice. All right, the ones are on here. All these numbers come out nice. Okay, there's no problem here. Upper triangular comes out with these. You notice here the minus zeros. That indicates. Remember we talk when I started talking about numerical methods. I said that there is a plus 0 and the minus 0. This is not a 0 clearly. It's a very small number. That's why we have the minus sign. But to the display is a 0. So here you see is the problem. You have 2 rows of zeros. That's the singularity of this matrix. But the other numbers come out correct, and there's no problem with this. I mean, like I said, this is the decomposition, which is acceptable. The permutation matrix is P2, and that's it. You can't solve anything with this. All right, it's pretty obvious from this. Remember, the first step in solving LU X is equal to B is solving this part with 2 rows equal to 0. There is nothing to solve here. You can't really solve this problem. Not this method, not the traditional way anyway, not this approach. The decomposition is successful. It's there. Okay, and if you multiply the 2, it will give you the original matrix. So this method doesn't fail. It fails when you abuse it, when you use it in the case where the problem doesn't really have a solution. Okay. Any questions before we go to the next step? Like I said, your next assignment is going to be to program Kraut's algorithm and solve a couple of some problems. So this time it's not going to be. This time the algorithm is important. It's not like Gauss elimination where we could. Now, by the way, it's in the instructions for the homework that I will post. That obviously you cannot, if you're going to solve problems, you cannot use LU decomposition. All right, from MATLAB. If I'm asking you to program this, you're not supposed to use this. You can use it though to check your answer. That's perfectly legitimate. Okay, that's why it's there. But the idea is that you will solve the problem using your own implementation of LU decomposition. I wouldn't wait for the last minute for this assignment because it does take some programming. It is not involved programming, but it is, depending on your experience in programming, this might cause you some difficulties. Not difficulties, but it's just regular programming issues. Okay. Any questions before I move on?
No.
I want to make sure everybody is okay before we proceed, not just 1 or 2 people.
Professor, is this document on Canvas by any chance?
I'm only going to put up the stuff that is on linear transformations. That's the only one. These are not.
Okay.
But like I said, for the algorithm, since I'm sure you didn't have time to take it down here. Okay.
Yeah.
This part that you will need, I mean, unless you have photographic memory, you can't get this. It's in the text.
Okay, perfect.
Yeah, it's if you type somewhere in the index, or if you go around and you say Kraut's algorithm, it's someplace. I don't remember where it is. I'm sure you can find it, but it's there. So you don't need, I just went through this in order to discuss it today, but you don't need this in order to, it's there.
Okay.
Okay.
Thank you. I'll look at the textbook.
Yeah, if you have trouble, let me know. I mean, I can look it up. I don't remember where it is, but it's there.
Yeah, that's fine. I have to read the textbook anyway, right?
You need a little bit.
Yeah.
Font this. All these nice equations with indices are nice, but you need to kind of, at least I find myself that I need to write a few out in order to see the trend or the pattern or exactly what it is. Okay. Yeah, unless you have any questions on this, let's move on to this topic, which is the final method for solving linear equations. I will not ask you to program this. This is a rather involved procedure. However, it is the go-to way, the go-to method for things of this kind, problems of this type. Yeah, the singular matrix. You might ask, well, what does it solve for you if this is a singular and it doesn't have a solution? Well, there is some kind of solution that is acceptable in some cases, and that's what singular value decomposition does. Before we go to that, we need to talk a little bit about inner products. So let's talk about inner product and orthogonality. This is going to come up again and again. This is a generalization of the inner product that you know from Euclidean geometry. In the same way that we did for transformations and for mappings and stuff like that, generalizing linearity and stuff like that. This is the same kind of thing extended to the inner product. Why is the inner product important? You may recall that two vectors in from mechanics, if you wish, or from simple vector analysis that you may have done. Two vectors are orthogonal or perpendicular to each other if their inner product is zero. The inner product for two vectors, right? Let's say you have these two vectors, right? Let's say this is B and this is A. The inner product A dot B, all right, it's equal to what? It's A, the magnitude of A, times the magnitude of B, all right, times what? Anybody?
Cosine theta?
Yes, the angle between the two. This is how it's traditionally defined in freshman physics, and it's used most of the time, all right? And theta is the included angle. It doesn't have to be in 2 dimensions. It can be in 3, it doesn't matter. It's the angle between the two. So if these are orthogonal, theta is pi over 2 and the cosine is 0, giving me that A and B are orthogonal if the inner product of these two vectors is 0. And that's usually used in physics. You know, if you have a block of stuff and you push and you pull it, you know, with the force F, the work is F dotted with the distance. So if the force is in the direction of distance, then this breaks down to F times D. But if F is this way, the work that does is 0 because it's perpendicular to it. The product is 0, so it doesn't really produce any work. This is the idea. Now we want to extend this to something that is not 2 or 3 dimensional, right? And we define the inner product not with cosines now because it's impossible to do that. It's possible to visualize, right? But it's again a very general function. Sometimes we denote it by angle brackets like this. Sometimes we denote it with just parentheses. It doesn't matter. X, Y. All right. Either way, these are different notations. We'll for this discussion here, we'll use the angle brackets. So the inner product is from V to V. V is the vector space where X belongs to. Bold letters are vectors, all right? So this is from X to X into R. So we take these two and we produce a real number. And what does this real number have to satisfy? The following things. for A in a real number, we have to have linearity, meaning if I have AX times Y, that's equal to A times the inner product of X and Y. So basically, if I scale X a little bit, so I scale the inner product. If they are X and Y is the sum of two vectors, then we have distribution. So it's A, Z, the inner product of X and Z, and plus the inner product of Y and Z. So these are conditions. These are fairly general. This is the linearity. We have symmetry. X dotted with Y is the same thing as Y dotted with X. And this is the most important part, okay, that is positive definite. If X dotted with itself is positive, and the only time that it is actually zero is if X is the zero vector. And this is an if and only if. In other words, X cannot be perpendicular to itself other than in the case where it's in fact identically equal to zero. All right, now with these restrictions, we have defined the inner product. And this is, again, interpreted in the same way as we have it in the in Euclidean geometry, all right? So in the terminology is there, if two vectors have, if X and Y have a zero inner product, then they're called to be orthogonal. Orthogonal or perpendicular. The more common term is orthogonal. All right, so if we write these as matrices or column vectors, all right, this, by the way, is true for infinite dimensional vector spaces, but we're not going to have to deal with that. But if for finite dimensional spaces, we can write these as column vectors, all right, and then for the inner products, X dot Y is the same thing as X transpose Y. So it's the sum of Xij times Yij. Xi, Yi, it's the sum of those two, of all those terms. All right. By analogy again to geometry, the norm, the Euclidean norm, is the same thing as X dotted with itself. All right. What is this? If we think of Euclidean geometry, it's x1 squared plus x2 squared. This thing is this plus x3 squared, and this extends to xn squared. All right, we don't have to worry about how many n's we have. Whatever it is good enough. Okay, so it's the length would be take the square root. Without we have the square of the length, and so that's the traditional norm. This is another relationship. All right. Now, a vector that has unit length is called unit vector, and it doesn't have to be along the axis. All right, anything that has a unit length can form as an axis, yeah, provided it's proportional, perpendicular to other n-1 vectors to form a basis. All right, now with this definition, now we have the following thing. Singular value decomposition is the method that we need to talk about. The reason that I wanted to talk about inner product is because for this method, the concept of orthogonality is crucial. Okay, so what is this method? It's a method for solving problems of all kinds where both Gauss elimination and LU decomposition fail, singular or very nearly singular. So, and the question is, of course, one has to think of it in the broader context. What does it mean to have a solution for a singular system? We need to interpret that and to see. I mean, it will give us a solution, but what? Okay, so what does the solution represent if it is not the unique solution that we were looking for? That's we need to understand. The other nice thing about singular value decomposition is that it tells you where the problem is with the matrix. It tells you where the ill conditioning is. It points out the rows and columns where you have a problem. And so it helps to troubleshoot problems if there are problems to be solved, or it isolates it and then it tells you how to go about. So it's a very nice and powerful method. It's used in a lot of cases, all right? And we'll see in just a minute, all right? It's also the best method for solving the least squares problems, and it's based on the following result that I'm just going to describe. recall that, does anybody remember the least square problem? We haven't talked about it, but anybody who's taken a lab has done this, some straight line fitting in data that have taken, in the lab. Basically, you have data. Let's say you have an independent variable and a dependent variable y, and you got data. Let's say this is a spring, and you measure the force required to extend it. This is the distance, and this is the force. So you get data points. Of course, unless you're cheating, they're not going to fall in a straight line. Okay, so you'll have them like that, and the task of least squares is to find out which is the line that best fits the data. And what does that mean? It means that there's the line where the sum of these distances, the squares of these distances, is minimal, and we get something. All right. If it's a spring, if it's a pendulum, we can get the period. You can do all sorts of things. All right, with this, it's a standard procedure. Is everybody familiar with this?
Yes.
All right. So I mean, we've seen it. I'm not asking you to do it right now. Okay. What is the situation here? Most often when you do an experiment like that, you have more data than, I mean, strictly speaking, if you're fitting a straight line, all you need is 2 points. But you're never going to do a spring, if you want to do determine the stiffness of a spring, you're never going to do 2 tests only, because you know that if you get this point and this point, you're going to get this as a curve, as the slope. If you get the data from this and this point, you're going to get this one. So neither of them is correct. And therefore, most often what we do is we get more data. Okay, so you get a situation where you have more than 2. Strictly speaking, to determine a line, all you need is 2 data points. Okay, a straight line passes through 2 points. But because of errors, we end up taking more. So what is the point? The point is that we have more equations, and then we fit the data, right? So we have that y is equal to mx plus c. All right. So we measure x, we impose x, and we measure y. So basically, we have curve fitting. So we have y1 is equal to mx1 plus c, y2 is equal to mx2 plus c. Down the line, yn is equal to mxn plus c. The bottom line here is we have n equations and only 2 unknowns if it is a 2-dimensional problem like this. So this is an overdetermined problem. We have too many equations and very few unknowns. This wouldn't have a unique solution. All right. In order to get a unique solution, you need 2 equations. Anything above is basically an overdetermined thing, and therefore it is possible that you don't have any solution whatsoever, or you have to do a compromise solution. What we usually find when we do experiment is we find a compromise solution, the one that minimizes that distance. That is the solution that SVD would give you for this problem, the compromise solution. I'm tying it to something that perhaps we're familiar with. So linear least squares is one of the problems that it does, but it doesn't have to be in this context. It could be, it solves the problem also where you have fewer equations, all right? You have m equations less than n. So you have more unknowns than you have equations, in which case, you have a singular problem. And there again, you don't have a unique solution, all right? So what does it do? It gives you the best possible solution in some kind of definition of best. And of course, it deals with a singular case of n by n. So it's kind of like a kill-all method, all right? It's expensive to run, and it's complicated. So if you have a well-behaved problem, LU decomposition is the way to go. You're wasting your time doing singular value decomposition if you have a nice, well-behaved and well-posed problem. So there's no need to resort to that. But if you do have problems with solving it this way, then singular value decomposition is the way to go. So it's based on the following result. All right, so let's go through it. Any questions before I proceed? By the way, MATLAB will also do this for you. Okay, it will do an singular value decomposition. all right? But you need to know what you're looking for, and you need to understand the nature of the problem in order to use it. So that's why what we're doing here. We're trying to find out what the nature of the problem is. Okay, so what does it do? This is a fundamental result. Let n by n be a matrix A. This is our familiar matrix A. And now let's suppose that we have m greater than n. Any m by n matrix can be written as the product of an m by n matrix U. Again, you notice that the theme here, we split it up into different portions in order to isolate the issues that are associated with the problem. All right, so it can be written as a product of an m by n matrix U, an n by n diagonal matrix W, whose entries are either positive or zero, and the transpose of an n by n orthogonal matrix V. Here's the term that we needed a discussion about orthogonality. I'll come back to what I mean by an orthogonal matrix V. In other words, what we have is that A can be written as U dot W dot V transpose. There is a reason for this notation that will become apparent in just a minute. U is m by n, of course it has to be, A is m by n, so this product has to give me an m by n matrix. These two, W and V, are n by n, both of them, right? And the nice thing also about W, it's also diagonal. And it has diagonal entries that are either positive, zero. Now, what is an orthogonal matrix V? An orthogonal matrix V, or any matrix is orthogonal if its columns are perpendicular to each other. So I have this matrix V that has n columns. Then this one is perpendicular to the other n minus 1. This one is perpendicular to the other n minus 1. In other words, if I write this as V1, V2, V3. So these are the column vectors of V. Then Vi transpose Vj is equal to 0 when I is different from j. And okay, so basically this is perpendicular to this. That means if these are orthogonal, by the way, this means that these are independent. Okay, so that's the idea behind V. All right. So this is what we have. U transpose U is equal to the identity. In other words, this is a characteristic. This is orthonormal, and so is V. Okay, and W has this form where some of the W's can be 0, and the identity matrix is 1 along the diagonal and 0 everywhere else. That's what this means. That basically means that U and U transpose are inverse of each other. All right. So the inverse of U is equal to U transpose, and the inverse of V is V transpose. That's what this means, because that's the orthogonality condition that you have. Okay. Okay. As indicated here, that's the nice thing, and this is the reassuring. I'm not going to prove this, obviously. We're not going to prove this because it's very complicated to procedure, and it's not really important for us right now. The nice thing about this is it can always be done. So like the LU decomposition, it can always be performed. What it tells you is another story, but at least it can always be done. Okay. We distinguish the following 3 cases. A is square. This is the problem that we've had so far, where maybe we have enough equations and enough unknowns, but in fact we don't have enough equations. The matrix is singular. All right. If all the matrices are involved as square, that means that that all of these U, W, and V are all square. All right. Remember, this is n by n, so this would be n by n. So if all of them are square, we have this first case. Then we have that A inverse is the inverse of this. All right. And do you remember how to do some matrix arithmetic. When you invert them, you reverse the order. So it's V transpose inverse. So this thing here is V transpose inverse times W inverse times U inverse. All right. And with these definitions that we had earlier, namely that V transpose V is equal to I, and U transpose U is equal to I. This simplifies to V. V transpose inverse. The transpose is the same thing as the inverse, so I recover V. Right? So V transpose inverse is equal to V transpose transpose, which is V. All right, so that takes care of this. The inverse of a diagonal matrix is a diagonal matrix which has the reciprocals as the diagonals, the entries. So it's the diagonal matrix with 1 over Wi along. All right, and U transpose is as indicated here. Okay, because U transpose is equal to U inverse. So we can write the A inverse as so. Now, immediately you see here where you see the problems where A might be. If A does not exist, then probably one of the W's is not a good one. Okay, it's 0. Remember that W's can be positive or 0. If the matrix is singular, you will have some zeros here, and that's the problem. Now, if a matrix is orthonormal, its inverse is, this is what I just described here. All right, so we have this. Now, how is this relevant to solving AX plus B equal to B is the following way. It explicitly constructs orthonormal bases for the null space and the range of A. Remember when we're talking about vector spaces, we talked about the null space and the range. The range is A is a transformation matrix, a mapping that takes from vector V to vector W to vector space W. Not all of W. Whatever the region that this reaches, that the transformation reaches, that's the range. The null space is when it takes everything to 0. It's the region in V that goes into 0. That's the null space. So the portion of V that is mapped to 0 by A is the null space. The portion of A that goes into the range the range is the region of W that V goes to under the action of A. So here's the thing. Is this too much terminology at the same time? Yes, no? Yes or no?
I think it's a little bit too much.
Okay.
For me, at least.
Okay, you guys ought to slow me down, or if you want me to explain this a little bit, you should. You shouldn't let me proceed assuming that everything is hunky-dory, because if it isn't, there is no point in me continuing. So let me backtrack a little bit, all right? And here's where we are, all right? Everybody's happy with this portion, the orthogonality and the...
Yeah.
Okay, so let's go. And here's the result. This is the main result. This decomposition here. Is everybody happy with this decomposition? The fact that this is true. Not that we have proven it, but the fact that this is true.
Yeah.
Okay, this is the orthonormal conditions. Like I said, normal means that the columns of A have norm 1, meaning have unit length. Orthogonal means that they're perpendicular. So orthonormal, for example, are the vectors I, j, k that we know. The familiar ones that we have in 3-dimensional. This is an orthonormal set of vectors. The columns of U under this condition here is a set of orthonormal vectors. That's what this means, because each one of them by itself, remember U U transpose would be U1, U2. This is the transpose matrix down to UN. Okay, U has columns U1, U2, U3, UN. When I form this product, what do I take? I take this one and I multiply with the first one. Because it's orthonormal, this gives me a 1, right? This gives me U11 times U11, U12, etc., etc. So this, because the matrix is orthonormal, this has unit length. Multiplied by itself, it gives me a 1. So when I multiply these two, the first one will give me 1. The U2 times U1, because they are orthogonal, will give me 0. U3 times U1, because it's orthogonal, it will also give me 0, and so on. So this is going to be 0. Now going to the second row, I have U1 times U2. That gives me 0 because of the orthogonality. And U2 times U2 itself gives me 1. So basically, this is what I have. Identity, a unit along the diagonal, zeros everywhere else. This is the identity matrix. That implies that U transpose is inverse of U. That's the definition of the inverse. So U transpose is equal to U inverse if U is orthonormal. If it's not, of course, this is garbage. Now you get to appreciate orthogonality of vectors and matrices. The same thing is true for V. If it's orthonormal, that's the case, all right? So we have these ideas about orthogonality here. Is this clear? How these are multiplied and what this implies?
Yeah, I see it.
Okay. So this is important because now, as you can see, this is what starts telling us. Remember how many of these we have independent and everything else. If they are orthogonal, they are independent, and that they start telling us what the null space is and what the range. We'll talk about just a minute. Okay. But essentially, when we have orthonormal set of vectors here in this matrix, that means that all these are independent and they span a certain space, being unit vectors. Think of them as unit vectors of something, of the range of this matrix. Okay, so now let's go back down here. The diagonal part, we know the inverse of this is 1 over W1. Okay, so are we all comfortable with this? Etc. I mean, all it takes is to multiply them again to see that this times this gives me 1. Right? So this is all right. So this is pretty clear, right? We take care of the inverses now because we have to do this inversion. Okay, so we have the following thing. So again, we're dealing with the square matrix. And the inverse now is done. The nice thing about this is now when A is square, all the matrices are square. And so we can write this way with this definition that I did, with this reverse multiplication that I did. Okay. So this is what we just showed here earlier. All right. So what is the relevance of this? Again, it's we replace A with this product. Then we can deal with it in portions. And then as we did in LU decomposition, we will see where we encounter the problem and where we encounter a meaningful solution and what it means, all right? Okay, so what is the bottom line? And we'll come back. I'm not gonna continue. We have 7 more minutes to finish, but this is the final result, all right? The columns of U, this is this one. Okay, remember our splitting is this. So the columns of U correspond to the non-zero elements Wi. In other words, Wi that has non-zero elements Okay. The columns that correspond to this, U1, let's say, these are columns that we're dealing with. U, K, UN. If we have non-zero elements here, they correspond to a certain columns here, right? The first one, W11 will correspond to the first one. WKK will correspond to the kth one column here. And WNN will correspond to the nth one and column here. Wherever we have a zero W, then we have a problem. Something is missing. But the rest of them that are corresponding to non-zero W correspond to a basis for the range of A. Remember that this is orthonormal, so all of these are perpendicular to each other. It turns out that the ones that we pick here that correspond to the non-zero W elements, the non-zero ones, not all of them, to the non-zero W's, form a basis for the range of A. So we can find the range of A just by looking at these. These would be corresponding. It's like looking at the X, Y, Z plane and say U1 and U3 correspond to these two vectors. The range of A would be the X, Z plane. We cannot get to Y because Y has a zero coefficient here, right? So we cannot get, however, our range corresponds to this. We have a three-dimensional vector space that's mapped by our matrix A into this. We can reach just the plane. That's the range. That's what this means. The columns of V now, okay, we have three of these. The columns of V corresponding to the zero elements, now we're having to deal with the zero ones, all right, are an orthonormal base for the null space of A. Remember that A takes some things from its own space, V, into V. Well, I don't want to use W because I used it here for the diagonal matrix. Into V, well, from V1, well, from V to, well, all right, from V to Y. Those are vector spaces, all right? This is the range of Y. The range of A is part of Y. The null space of A is the portion of V that gets mapped into zero. It doesn't go into Y, it just gets mapped to the origin. Now, for the same reason that we had a basis for the range in here, we also have a basis for the zero, for the null space. So the null space here has a certain dimension. It corresponds to the number of elements in W that are in fact zero. Let me stop here because this is might have overwhelmed you. And maybe what I will do on Wednesday is actually, instead of using the stupid mouse, I'll use the iPad to do a geometric representation. The best way to deal with this is to actually do some geometry to the degree that it's possible. Okay, by giving examples like three-dimensional or two-dimensional plane. So we will come back to this on Wednesday. Don't worry about getting this yet. And I will elaborate these ideas, the columns and the columns of V corresponding to one, and then what it takes to solve AX equals B, because that's our objective, right? Our objective is to solve AX is equal to B. All this stuff is frivolous if it doesn't do anything for us. Okay, so let me stop here, and if you guys have any questions, I'll be happy to answer them, including this, but we will come back and revisit this. Do you find this kind of overwhelming?
It's a lot of information. I think if we go over it on Wednesday, I think I'll understand it a lot better.
Yeah, and I think you should maybe think about it. What kind of quick discussion we did here today. Maybe you can ask me questions. I mean, I think that's the best way. I don't want to presume that you know things, and I don't want to be, repeating things that everybody knows. So I'm not quite sure where you are. And the problem is, most likely, some people are more knowledgeable than others. That's understandable, given that we have a fairly diverse group, and this is a little bit theoretical, if you ask me. However, it is important in understanding the method. That's all. I think the best approach is to think like geometry. That's the idea, and I will try. I will try to deal with these ideas, what these vector spaces are. And I'll put out that discussion, although it's again just a summary of things about linear transformations. That's the idea here. That's why I wanted to discuss that last time, and I didn't put it on Canvas. But that's the reason why I wanted to discuss the idea about null spaces and vector spaces at the time, because I knew it was coming because of this discussion. It plays a central role here. But I think it's important not to go algorithmically and try to understand how to get this decomposition, but I think it's important to understand this method because it's the go-to method for the cases where everything else fails. And that's not an unusual case. Okay? All right, let me stop the share. Please don't get intimidated with this. It's not as complicated as it sounds. I think we can make more headway on Wednesday.
Sounds good.
Any other questions? All right. So I'll see you on Wednesday. Bring your questions. All right? Don't expect me to guess where you're missing something, because I you know, it would be hard in class. It's even worse here. All I see is blank screens. I can't guess where you are. Okay. All right. So you guys have a good evening, and I'll see you on Wednesday.
Thank you, you too.
Thank you,
Thank you,
Professor.
Professor.